Ephemeral black holes are theoretical, microscopic black holes that could be briefly created under extreme conditions, such as in high-energy particle collisions within particle accelerators like the Large Hadron Collider. Unlike the massive black holes in space, these would be incredibly tiny, lasting for fractions of a second before evaporating through a process called Hawking radiation. The idea stems from theories that suggest extra dimensions or high-energy scales could lower the threshold for black hole formation. When particles collide at nearly the speed of light, the concentrated energy could curve spacetime enough to create these miniature black holes. For example, if the energy levels achieved in the LHC were sufficient and certain extra-dimensional theories are correct, these black holes could form and decay almost instantly, releasing unique particle signatures. Imagine smashing two marbles together so hard that they briefly form a tiny vortex before disappearing, leaving ripples behind. Studying ephemeral black holes would offer insights into quantum gravity, extra dimensions, and the fundamental nature of spacetime, providing a bridge between general relativity and quantum mechanics.
Ephemeral black holes, also known as micro-black holes, are theoretical black holes that form under extreme conditions of energy density, but exist only for incredibly short periods before evaporating. Unlike the massive black holes found in space, ephemeral black holes would be microscopic, with sizes smaller than a proton and lifetimes on the order of 10⁻27 seconds. Their formation relies on specific extensions of physics beyond the standard model, such as the presence of extra dimensions or quantum gravity effects. In high-energy particle collisions, like those at the Large Hadron Collider, LHC, particles moving near light speed could create energy densities sufficient to form an ephemeral black hole, provided theoretical conditions like extra dimensions are met. Ephemeral black holes are like tiny whirlpools that form momentarily when two drops of water collide, disappearing almost instantly but leaving ripples that reveal their presence. The concept of ephemeral black holes arises from theories like string theory and the brane world scenario, which propose that our universe has additional spatial dimensions beyond the familiar three. These extra dimensions could reduce the threshold energy required to form a black hole. According to general relativity, a black hole forms when energy density is high enough to warp spacetime into a singularity. In particle accelerators, colliding particles at energies approaching the Planck-scale, 1019 GeV, could theoretically create these conditions, especially if extra dimensions amplify gravitational effects. In a five-dimensional brane world scenario, the energy required to form a black hole could be orders of magnitude lower than in a purely four-dimensional universe, making it feasible at LHC energies. Extra dimensions are like hidden shortcuts that make it easier to dig a tunnel through a mountain, reducing the energy needed to reach the other side. Once formed, ephemeral black holes would rapidly decay via Hawking radiation, a process where black holes emit particles due to quantum effects near the event horizon. This evaporation happens extremely quickly for microscopic black holes, as their lifetimes are inversely proportional to their mass. The decay releases a distinctive burst of particles, including photons, neutrinos, and potentially exotic particles, providing a unique signature for detection. If an ephemeral black hole forms in a particle collision, its evaporation could produce a spray of particles detectable by instruments like those at the LHC. Hawking radiation is like a block of ice in a hot pan. It evaporates almost. Particle colliders like the LHC achieve extreme energy densities by accelerating protons to nearly the speed of light and smashing them together. If the collisional energy exceeds the critical threshold for black hole formation, and if the right theory, these black holes would decay into a burst of particles, creating an observable pattern in the detector data. The ATLAS and CMS experiments at the LHC are designed to search for unusual events that could signal the creation and decay of micro black holes, such as excess particle jets or missing energy patterns. Creating ephemeral black holes is like colliding two symbols with such force that they produce a fleeting, barely perceptible shockwave before the sound dissipates. Detecting ephemeral black holes requires identifying their particle decay signatures, which differ from those of standard particle interactions. These include high multiplicity particle jets, a spray of particles emitted isotropically from the decay, missing transverse energy, if neutrinos or other undetectable particles are produced during decay, Planck-scale resonances, patterns indicating the involvement of gravitational effects at quantum scales. At the LHC, detectors like CMS and ATLAS analyze trillions of collisions for anomalies in particle production rates and energy distributions. Detecting ephemeral black holes is like searching for a firefly in a storm. It's fleeting, but leaves a distinctive glow amidst the chaos. Ephemeral black holes provide a unique experimental window into quantum gravity, the elusive theory that unites quantum mechanics and general relativity. By observing how gravity behaves at the smallest scales, researchers can test hypotheses about the quantum structure of spacetime, validate or refute theories like string theory, and explore the properties of the Planck scale. If black holes were detected at energies lower than expected, it would suggest the existence of extra dimensions or other new physics. Studying ephemeral black holes is like cracking open a tiny safe to glimpse the fundamental blueprint of the universe. If ephemeral black holes form in accelerators, they could confirm the existence of extra dimensions proposed by theories like the Randall-Sundrum model or string theory. These dimensions could alter the behavior of gravity at small scales, allowing black hole formation at achievable energy levels. If black hole formation is observed at LHC energies, it would provide indirect evidence for the existence of hidden dimensions curled up at subatomic scales. Discovering extra dimensions via black holes is like finding a secret hallway in a seemingly ordinary building, revealing an entirely new architectural structure. The creation of ephemeral black holes is speculative and hinges on unproven theoretical frameworks. Additionally, the energy levels currently achievable in particle accelerators are orders of magnitude below the Planck scale, making detection extremely challenging. There are also public misconceptions, with fears that creating black holes in labs could lead to catastrophic events. Though rigorous calculations show these black holes would evaporate harmlessly and instantly. The LHC has not yet observed ephemeral black holes, suggesting either that they require higher energies or that extra dimensions do not exist as theorized. Searching for ephemeral black holes is like trying to find a needle in a haystack while unsure if the needle even exists. As particle accelerators become more powerful and detector technologies improve, the search for ephemeral black holes will continue to push the boundaries of high-energy physics. Discovering these black holes would confirm the quantum nature of gravity, provide evidence for extra dimensions or string theory, and offer insights into the early universe, where similar high-energy conditions existed. Proposed upgrades to the LHC or future accelerators like the Future Circular Collider, FCC, could achieve the energy levels necessary to probe deeper into black hole formation.